Hey, hang on a minute. I guess we're live. Hi, everybody. Hello, everybody, and welcome to our session. I'm Zong Yang, your tutor for today, and welcome to our second ever live streaming session for Homeschool.Asia. Today, we'll be solving the entire paper for the IGCSE Physics subject code 0625, Winter 2025, Paper 4, Set 1. So for our session today, we'll be going through the entire question paper and explaining how to solve each question in detail. I hope everybody here finds this useful. Please take note that we will be answering 15 appropriate questions from the live comment section regarding the paper we are going through and other IGCSE physics questions on a first come, first served basis. These questions will be vetted by our physics tutor, answer. So please do submit your queries if you have any. Now, without further ado, let's begin with today's session. Right. I think everybody should be able to see our screen now. Okay. Right. Without further ado, let's begin. All right. So let's begin with today's first question for paper 4, set 1. All right. So as per usual, for all IGCSE physics papers, right, the first question usually got to do with kinematics. So in our first question over here, a train travels at a constant velocity of 56 meters per second on a horizontal track. So the mass of the train is 440,000 kilograms. All right, so we do have a few important values to take note here. Number one, the speed of the train, sorry, not speed, the velocity of the train, which is 56 meters per second, and the mass of the train, which is 440,000 kilograms. Right, so usually in the first part of the questions, we will need to determine what's the difference between a scalar and a vector quantity. So as you can see over here, right on the money, we are to state the difference, right? So the command word is state. State meaning you just need to say what's the difference between the velocity of the train and the speed of the train. Okay, so this is a very simple question. Simply put, velocity is a vector quantity, while speed is a scalar quantity. A vector quantity has a direction and a magnitude, while a scalar quantity only has a magnitude. All right, so let's write down the answer very, very simply like this. Right? Right? Instead of, instead of us, just writing down everything very, very slowly over here, let's just stick to this. Okay? So let's write down speed is a scalar quantity, while velocity is a vector quantity. There are also several other different answers for this. For instance, velocity is the speed of the train at a particular direction, or velocity has a direction, while speed does not have a direction. All right. Okay, so that is our first 1 mark done. Simple, right? Okay, next, let's move on. We either calculate the kinetic energy of that's stored in the moving train. So do remember, kinetic energy is the energy of an object traveling at a certain velocity. All right, so if you remember the equation for kinetic energy is equals to half times mass of the object times velocity of the object squared. This is how you write the equation. So half multiplied by 440,000 kilograms multiplied by 56 meters per second squared. Now let's punch the calculator and you'll get a really, really large number. 689,920 and 000. Now here's the thing, right, is that Cambridge don't really like big numbers like this. You want to move everything to at least two significant figures. All right, so let's do everything into two. Let's convert this to two significant figures and also into standard form. So let's first convert this to two significant figures, which is 690, because 9 is greater than 5. We want two significant figures, which is 6 and 8 here. So since 9 is greater than 5, we add 1 to the 8 here, and we convert this to 0. So it becomes 690, 000, 000 joules. Okay. Now, we also want to convert this into standard form because there's so many zeros here that makes presenting everything very difficult and very unwieldy. So let's calculate the number of zeros here. So you have, this is the, let's say here's the decimal point. So we have 1, 2, 3, 4, 5, 6, 7, 8. We will, let's move here, equals to 6.9 times 10 to the power of 8 joules. Okay, let's write that down. Remember, the unit for energy is joules, J. 6.9 times 10 to the power of 8. Please write that down. All right. So for this question, it has 2 marks. So simply writing down EK equals to half mv squared gets you 1 mark. Getting you the correct answer, right, gets you 1 mark as well. And that gets you your 2 marks. Easy peasy, yeah? All right, let's move on. Next, the train has a uniform deceleration of 1.2 meter per second squared. So we are to, okay, so deceleration of 1.2 meters per second squared. All right, so we need to calculate the constant braking force, which brings the train to rest. So we are supposed to calculate a force, right? And we are also given deceleration. Now, how do you calculate force? It's very simple. We use Newton's second law of motion, or we use F equals to mass times acceleration. All right, we have been given the mass of the train already, which is down here. It's equals to 440. So do remember, mass is equals to 440,000 kg, right? And we have the deceleration. Essentially, deceleration is negative acceleration, but in this case, we will just use it as deceleration of that. So for this, right, the we didn't determine what is the direction, so this is fine. So let's find the force. 440,000 multiplied by the deceleration of 1.2, right? Beg your pardon, this is needs to be properly annotated. And now with this, you do some mathematic trickery, we get 528,000 newtons. And of course, converting this into two significant figures, we get 530,000 newtons. Do take note, newtons is the unit for force, all right? Please remember to write that down. All right, so how do you get your full 2 marks here? Well, that's pretty simple as well. Firstly, once you recognize that you can use Newton's second law to solve this question, you get 1 mark here. And when you calculate the correct number over here with the correct significant figures, we have another mark here. That gets you the full 2 marks. Okay, pretty simple, isn't it? Okay, so let's move on to the last part of question 1. We need to calculate the distance traveled by the train as it comes to the rest. So we need to calculate the distance traveled by the train. So this question is a little bit more tricky. We want to take a look at, there are 2 methods to complete these kind of questions actually. So the first method is to use either work done. The second method is to use kinematics. So let's use the first method to calculate the distance traveled, which is work done. Okay, so let's use work done. All right. So first things first, we already have the work done, W equals to force exerted multiplied by the distance traveled by the train. Okay? Right. So where do we get this work done? Okay? Work done, the work done over here is determined by, it is basically the energy required to actually stop the train from moving until it completely stops. All right? But here's the thing now. Now you get asked, right, teacher, how do we know that? Right? So we need to know that the initial energy of the train is what we have calculated over here. So kinetic energy of the train is 6.9 times 10 to the power 8 joules, right? This is the initial energy. Now, the final energy is when, when the train stops. And when the train stops, there is 0 joules. Okay? So, the work done is simply this energy minus 0. And this is the energy it takes to stop a moving train at this speed. So, simply put, we can tell that, right? It is the energy for the train from moving to rest. So let's find this first. Let's write down. Work done, right, by brakes. Stop the train. Right, is equals to the change in energy for train moving. Okay, so a change in energy for a train from moving to rest, and that gets you 6.9 times 10 to the power 8 joules. That's the first part of the question. Second part of the question, we can use work equals to force times work done is equals to force times distance. So let's do this. Right? Work done is equal to force times distance. We want the distance traveled by the train. So we move force over. We divide force by on both sides. So distance is equals to work done over force, which is equals to 6.9 times 10 to the power of 8 divided by the force, which is up here, 530,000 newtons. And doing the mathematics, we get 1.30 times 10 to the power of 3 meters. And of course, converting this using only two significant figures, you get 1.3 times 10 to the power of 3 meters. Okay? All right, so let's write the answer down. Please remember to include the SI unit for distance, which is meters. Okay? Oops, that's way too many waves. Oh, I'm so sorry. The working is being blocked by the banner. Let me just move it up a little bit. Thank you so much, Naransa, for highlighting that. All right, so this is our answer. Do remember to please do remember to write your units, as this is very, very important. All right. So how is this 3 marks given to you? It's very straightforward. The first mark is given, right, if you recognize, right, that work done is equal to force times distance, or distance is equal to the work done divided by the force. Okay. Right. Now the second mark is given, right, when you recognize the change in energy is equal to 6.9 times 10 to the power of 8. Gives you a second mark. And the third mark is given when you get the correct answer over here. And gets you the full 3 marks. Okay? So now we have done with method number 1. Right? But there's a second method as well that I would like to also highlight very quickly. Right? So the second method we want to use is the deceleration and speed of the train. Okay? So since the deceleration and the speed of the train is provided, so the deceleration is given over here, 1.2, and the speed of train is 56 meters per second. Okay. Right, so we can find the time taken by doing this. We can find the time taken for the train to decelerate to fully at rest, which is you take 56 divided by 1.2. So time taken is equals to 56 divided by 1.2, which gives you 46.66 seconds, right? And since this deceleration is constant, we can find the average velocity. Okay, again. That works better. Okay, that's a bit of an issue. So we can find the average velocity by dividing 56 over 2, which is 28. And then we can find the distance simply by taking the average velocity, which is 28, divided by 46.66 seconds, which gets you 1.3 as well. Oops, my bad. Which gets you 1.3 times 10 to the power of 3 meters. Right? Okay? So the second method is a little bit more, it takes a bit more time to guess, but I think both methods do work for this. All right. Everybody good? All right, fantastic. Let's move on to our second question of the day. Right, so we have 10 questions today. So please move on with let's move on with the second question. After the second question, please feel free to ask any questions if you have any. All right. All right, let's move on. Second question. It's a little bit strange, right? The second question has given you information of the planet Mars, right? And if you use this table, it's giving you the mass of Mars, the gravitational field strength, and the average density. All right. So this question is asking you for, this question is asking you for several things. That is related to density, mass, and gravitational field strength, right? So the first part of the question asks you, wants you to define gravitational field strength. Okay, now this is a bit of a problem. It's a bit of a problem. All right. Now you have never learned in the syllabus for in the syllabus for IGCSE Physics, right? We kind of never really learned what is gravitational field strength. Okay, so in this case, we have to make do and look at the units of the measurements here. As you can see, gravitational field strength has newtons divided by kilograms. So newtons is basically force and kilograms is mass, right? So since gravitational field strength is basically Newton, the units of gravitational field strength is newtons per kg. So we can kind of guess that gravitational field strength is literally force divided by mass. So let's write that down. Right. Right, so as you can see here, gravitational field strength is defined as the force per unit mass on an object in a gravitational field. Pretty straightforward, yeah? Okay, so remember, force divided by mass. Okay, right, I have a question from Narayan sir. I'll get back to you later once I'm done with question 2. All right, thank you so much for the heads up. Yeah. Increase volume a little bit. Is this better right now? I have maximized my volume. Can everybody hear me? That's interesting. This is as loud as I can try to be. Okay. All right, fantastic. Then let's move on with the next part of the video, of the question, right? So now let's move on to part B1. Okay. So an object has a weight of 42 newtons at the surface of the Earth. So we are to calculate the weight of the object at the surface of Mars. Okay. So, right. As you guys know, the weight of an object, right, can vary according to the planet, or it can vary according to the gravitational field strength of the planet, but the mass of the object will remain the same. So the first step to determining this is to find the mass of the object. So as you know, the mass of the object over here, as you know, weight is equals to mass times gravitational field strength of the surface we are standing on. So let's move mass over here. Mass is equals to weight divided by gravitational field strength of Earth. If you guys remember, gravitational field strength of Earth is equals to 9.8 meters per second squared. Okay? Right? So, oh, we have a guest. Hello. All right, sorry, you can't be here. I had to move you down. All right. Okay. Well, yes. The gravitational field strength of Earth, as described by Cambridge, you have to use 9.8 meters per second squared. Okay. 10 is the old syllabus. 9.8 is the current syllabus. So please remember that. This is written in the front of our worksheet, as you see here. Right. Take the weight of 1 kilogram to be 9.8 newtons. So this is what you need to take note of. Okay, 9.8 meters per second squared. All right. Fantastic. That's a good question, by the way. Okay, so now we are done with that. All right, let's do this. Equals to 42 divided by 9.8, which gets you 4.285 kilograms. That's the first step done. Now, let's move on to the second step, which is we need to calculate the weight of the object on Mars. So let's use this again. Weight is equals to mass multiplied by the gravitational field strength, and this is Mars, okay? That is 4.8285 multiplied by this thing, gravitational field strength at surface, which is 3.7. And doing the calculations, you get 15.85. And doing the calculation, doing the conversion to two significant figures, rounding it up, we get 16 newtons in two significant figures. Right? Yeah, so let's do that. 16 newtons. Please remember, the weight of an object is measured in newtons. The mass of an object is measured in kilograms. Okay, all good? Yeah? Okay, very good. Right, so with that part done, please take note, right, that for this question, the first mark is given when this 4.285, when you calculate the mass of the object, you get 1 mark. And when you get the correct answer, you get the second mark for a total of 2 marks. All right, fantastic. Let's move on. All right, let's go. Let's move on. Now, part 2, we are to calculate the volume of Mars. Okay, so the volume of Mars, we have the density and the mass. As you guys know, the volume is, the density is equals to mass divided by volume. So as we see here, density, as we use rho over here, is equals to mass divided by volume. So if you want to find the volume, you multiply volume on both sides, volume, and then you remove, then you divide rho on two sides. So it'll be equals to mass divided by density. And now let's bring in the values from the table. Mass of Mars is 6.4 times 10 to the power of 23. Right, divided by the density of Mars, which is 3,900 kilograms per meter cubed. 3900. Okay, that's very good. Calculate the volume, and doing these calculations, you get 1.64 times 10 to the power of 23. All right, this is in meters cubed. This is the unit for volume. Now, we have to make sure this is in, of course, in two significant figures. So we will need to round this downwards because 4 is lower than 5, smaller than 5. So it's 1.6 times 10 to the power of 23 meters cubed. That's our answer. Okay, in two significant figures. That is very bad handwriting, my bad. Times 10 to the power of 23 meters cubed. All right, so how do you get the full 2 marks of this question? First, you must identify the values here. Volume is equals to the mass of the object divided by the density. And second mark is given when you get the correct answer over here to get the full 2 marks. Right? Okay. Very good. Now let's move on to part C. Wow, all Mars stuff. I think the Cambridge people today really liked Elon Musk, huh? All the fascination with Mars. All right, let's move on to part C. Okay, now part C shows a space buggy that is tested on Earth, and the buggy is traveling at a constant speed in a straight line. The driving force, as written over here, is 30 newtons. Okay, right. So we are to draw one arrow to show the size and direction of the resistive forces on the buggy. Okay, so the key here, if you can see, right, is the constant speed. And there's also a driving force of 30 newtons. So, as you know, constant speed equals to no acceleration nor deceleration, which means all the resultant force of the buggy is 0. So, what that means is, right, the arrow on the buggy, right, should be the same. Oops, my bad. The arrow on the buggy should be the same size as the arrow of the should be the same size, actually, and opposite direction. Pardon me, I can't seem to draw a very straight line on this darn thing. Yep. Okay, just assume this thing is the parallel to this to the driving force. Yeah. Okay. So it should have the same magnitude, which is 30 newtons, but pulling the vehicle behind. So basically, the driving force on the buggy should be equals to the 30 newtons of the resistive forces over here. Okay, so this is your first mark. So you have to draw one arrow, which is over here. That's your first mark. And the size and direction of the resistive force, which is 30 newtons, this side. So this is the second mark. And that gets you your full 2 marks. Okay? All good? Fantastic. All right. Now, the air resistance on Mars is low. Now, let's go to C part 2, sorry. Right? The air resistance on Mars is less than the air resistance on the Earth. So, we are to state what this effect has on the resultant force on the buggy on Mars. Okay? So, as you know, Mars has less dense air than Earth. And the buggy over here still has the same driving force of 30 newtons. So on Mars, since it has less air resistance, right? So the resistive forces is less than what is experienced on Earth. So what does this mean? Right? This means that, right? Okay, let's see. Let's state the effect this has on the resultant force on the buggy on Mars. So this means, right, since now the resistive force is less than the driving force, there is now a resultant force over here. This effect, so there is a resultant force. Okay, there's a resultant force acting in the direction of the driving force. Okay, let me just write that down using text. That should be better. Pardon the horrible spelling mistakes. Right, so there is a resultant force in the direction of the driving force. All right, simply because the resistive force over here, right, is less than the driving force. Okay. Good. Now, let's move on. Okay. Now, next thing, we want to state the relationship between resistive forces, the driving forces, and the resultant force. So, basically, we want to state the relationship between this force, and the resultant force over here. So, that's not as you can see over here, right? On stage 1, when the buggy is on Mars right now, okay, the driving force is 30 newtons, and the resistive force is less than 30 newtons. So that means there is a resultant force acting this direction. Okay. Resultant force acting on this direction. So what we do know is the resultant force over here should be equal to the driving force minus the resistive forces. Okay, as straightforward as it gets. Pretty simple, isn't it? Okay, so with that done, that is another mark settled. Another point, another mark done. Okay, so unfortunately, part 2, right? You need to have both correct in being able to get that 1 mark. Oh, so just a quick tip for you, for all students. If you are rushed for time and there's a lot of things in your write for very few marks, you can kind of skip this if you don't have time to write. Okay, yeah. Now, before we ask more questions, I'd like to quickly add on to something over here for part 1, for question 1, part C2. Okay, so as Narayan sir has stated over here, do take note, right, that the distance traveled by an object is equal to the average velocity divided by the time taken, right, as we have known here. But how do we know this is the average velocity? Well, as you can see in this graph, this is the velocity of an object. This is the this is the velocity of the object, and this is the time of the object, right? So in for an object going through constant deceleration, right? Okay, this is the speed as it's currently going, and this is the time, right? As now, to find the average velocity, you know that, right? You can just take the whole the difference between the velocity over here and the velocity over here, and then take the difference between these two velocities and divide it by 2. So the velocity here is 56, and this is 0. So 56 minus 0, and then divided by 2. Oh, I'm so sorry. Distance is velocity multiplied by time. My goodness, I made a mistake here. Thank you so much. Thank you so much, Narayan sir. I made a very silly mistake. So basically, where was I? Yeah. So over here, you can find the average velocity over here by taking 56 divided minus 0 divided by 2, and that gives you 28 meters per second. Okay. So thank you so much for catching my mistake, Narayan sir. That's fantastic. I can be very careless at sometimes as well. I'm a teacher, I know, yeah? So not to worry. So this happened to me as well. Oh, all right. So do remember, the average velocity of an object undergoing constant deceleration can be found by taking the initial speed, right? Initial velocity minus the final velocity divided by 2. Okay, now, oh, thank you. We have 2 questions. All right. So, Mr. Avash Thapa. So, your question here goes, F is equal to G M1 M2 divided by D. Can I explain anything about this? As much as I know about it, unfortunately, the IGCSE syllabus does not teach the laws of gravitation. So unfortunately, I'm unable to explain your question. I'm so sorry about that. But thank you for sending in your question. And as for Saurabh Shrestha, yep, your mass come up to exactly 4.2 kilograms and the weight of the object on the Mars is 15.5 newtons. All right, so over here, you got 15.5 newtons over here, and your mass is 4.2. So, what happened over here, right, is very simple. When you calculate your mass over here, you want to leave as many decimal places as you can as your intermediate working answer, because if you round up now, right, you'll mess up the answers in the end. So, for example, when I find my mass over here, right, you should be taking 42, which is the weight of the object on Earth, divided by 9.8, which is the gravitational field strength of Earth, to get 4.285. During this part of the working, please do not round up or down anything, right? We take the raw answer, put it into our second working, and you should get 15.85, right? So 15.85 newtons. This is when you then do your rounding up or down to your 2 significant figures, so on and so forth. Do remember to do only this rounding up or down at the end of each question, okay? At the end of the question over here. All good? All right, that's fantastic. Thank you for sending your questions, Saurabh and Avash. Thank you so much. Now, without further ado, let's move on to question 3. 1 second. I'm human. I need to drink water. All right. Now let's move on to question 3. All right. Question 3 shows a simplified diagram of a solar cell. Ta-da, over here. All right. So in this solar cell, we are to describe the energy transfer of the solar cell in the solar cell. Okay. So over here, as you can see, this solar cell has let's see over here, right? It has a conducting material. It has a black coating, positive and negative contacts, and is connected to a circuit involving a voltmeter. Okay, so we are to describe the energy transfer in a solar cell. So this is simply put light energy, okay, and this light energy is converted into electrical energy. So pretty much that's our answer. It's very, very straightforward, right? So light energy from the sun is converted into electrical energy, and that gives you your full 2 marks. How so? So the first part they are looking for is light energy from the sun. And the second part, the second mark you get from is converted to electrical energy. And having these 2 different energies gives you your full 2 marks. Easiest 2 marks ever, isn't it? Right? So part B, the question asks, right, suggests how the black coating, all right, of the solar panel allows the solar cell to transfer more energy. Now, the clue to this is black coating. As you remember, for heat transfer, right, for objects that are shiny, objects that are black, it absorbs more energy. Objects that are shiny, it reflects away the radiation. So black objects absorb radiation, shiny objects reflect radiation. Also, black objects radiate better compared to shiny objects. Okay, so the part we need to learn from here, or the part that we need to write down from here, is that black objects, right? Since it's black, right, it absorbs energy better. So without further ado, let's write that down. Okay, so black is a good absorber of radiation. End of story. Okay, yeah. Of course, there are other options. There are other answers for this. For example, black also, you're also able to reflect less light compared to other colors. Okay, so that is our main answer. Black is a good absorber of radiation, and that gives you your 1 mark. Don't overwrite this. Even though they give you 2 lines to write, you just need to have one good point for this. Okay, good, yeah. Okay, fantastic. Let's move on. Part C. Right, so for part C, we have some calculations to do. Now, we are given that 0.72 kilowatt of light is incident on the solar cell, which means 0.72 kilowatts of light shines on the solar cell. All right, and the cell has an efficiency of 75%. So we are to calculate the output power of the cell. All right, actually in real life, this is not possible. Just a fun little fact, okay? Yeah. So we need to calculate the power output of the cell. So input is 72. Okay. E input is 0.72 kilowatts, right? And we have an efficiency of 75%. Now we can find the output. Let's do this. So first thing first, let's use this equation. Efficiency, my goodness, 1 second. Right, is equals to the input. Oh my goodness, my bad. Is equals to the output divided by the input multiplied by 100%. Okay, so we have the input over here, which is 0.72. We also have the efficiency, which is 75%. So let's just move everything over to this side. Okay, so we have the output is equals to, right? Output is equals to efficiency divided by, not divided by, multiplied. Okay, equals to input multiplied by the 75% over here. All right, and that gives you 0.72 multiplied by 75%, and that gives you 0.54 kilowatts. Okay, right, so let's write that down. Zero 0.54 kilowatts. That's better. Okay, so in 2 significant figures, so I think this is done nicely for us. Fantastic. All right. Okay. Right, now we have found this answer for the output power. We need to move on to C part 2, and we need to state the meaning of the term kilowatt hour. All right, so kWh. So what exactly is a kilowatt hour? So a kilowatt hour is actually a measure of energy used. Right, energy. It's a measure of energy, okay? And this energy is basically the amount of power, which is in kilowatts, used in an hour. Okay? So let's write that down in nicely written text instead of my horrible handwriting. The kilowatt hour, right? We have a dash here, is the amount of energy used or transferred by a 1 kilowatt device in an hour. All clear, I guess? So, yeah, there we go. Okay, so that's pretty simple, yeah? Okay, let's move on to C part 3. All right, so here, the energy produced by each solar cell, as we've seen up there above, is for an average of 6 hours a day. It's used for, oh my goodness. All right, sorry, let me rephrase this again. Energy is produced by each solar cell for an average of 6 hours per day. So it's been used for 6 hours for each day. And the household used approximately 7,400 kilowatt hours of energy per year. So we have to calculate the number of solar cells needed to produce energy for one household. Right? Number of solar cells to produce energy. Okay? So we have been given we have already calculated the output power of the solar cell, which is 0.54. So let's write that down first. Kilowatt, yeah, 0.54 kilowatts. Okay. Now, there are actually several ways. There are several different methods to work on this, but let's use my method, which is pretty straightforward, right? Okay. So we first bring down the output of our cell, which is over here. Okay. And we know that each cell produces power for 6 hours. So let's just say okay, 6 hours. So let's find out what is the energy output of one cell per day. Okay, that should be equals to 0.54 multiplied by 6 hours, and that gets you 3.24 kilowatt hour. Okay, that's our first step. Now, second step, we have to find the energy output of one cell in a year. So let's do this. That should be get you 3.24 multiplied by 365 days. Okay, we already found one day it produces this many kilowatt hours. So that gets you 1182.6 kilowatt hours in a year. Okay, and finally, we know that, right, one house requires 7,400 kilowatt hour per year. So we need to find the number of cells, right, that's needed to power a home for a year is be equal to this, which is the power you need for a year, 7,400 divided by 1182.6, which is the energy output of one cell in a year, right? And that gets you 6.257. Okay, that is the rough working. But however, you can't say 6 cells because 6 cells will not produce 7,400. You must have 7 cells instead. So we must round it up. So you must round it up. Okay, so the final answer is 7. 7 cells. Okay. All right, so this is the method to find the number of cells you need to power a home that uses 7,400 kilowatts hour per year. All right. Then with that done, let's move on. We are done with question 3. All right, let's move on. Let's move on to question 4. Okay, question 4. So question 4 is testing you on latent heat. Is testing you on specific heat capacity. All right. So over here, a 12-volt 50 watts immersion heater is used to heat up 0.15 kilogram of water in a beaker. And the water is initially at a room temperature of 20 degrees Celsius, and we are given the specific heat capacity of water. Right, so we need to calculate the energy supplied to raise the temperature of water from 20 to 58 degrees Celsius. All right, so let's find out what are the things you need over here. So firstly, we have the mass of water, which is this. Okay, this is very well needed. We need the specific heat capacity of water, which is this. Okay, and we need to find the change in temperature. Do you remember we have this equation, right? Change in energy is equals to mc delta theta, right? Where m is the mass of the object, E is the energy required, C is the specific heat capacity of water, and delta theta is the temperature. So let's find everything one at a time. We have the mass found, which is over here. We have the change in temperature we need to find right now. So let's do this. Change in temperature is equals to 58 minus 20 degrees Celsius. And that gets you 38 degrees Celsius. Right, so it's 38 degrees Celsius for the change in temperature. We found that now as well. Specific capacity of water is found as well. Now we need to find the energy supplied. Okay. So we can now put in each of these values to find the energy supplied. So 0.15, okay? Is the mass multiplied by the specific heat capacity, 4200, multiplied by 38, which is the change in temperature. And that gets you 23940 joules. And of course, let's round this up to two significant figures, 24 joules. Okay. Yeah. Okay. Right, so there we go, two significant figures. Okay, so let's write that down. Almost humongous. Let me just. Oops. Oh. Go. Okay, fantastic. So how do we get the full 3 marks here? So the first mark will be given if we find the change in temperature. Okay, second mark is given if you know this equation for specific heat capacity, and the third mark is to get this correct. You get your full 3 marks. Okay, right, let's move on. As you can see here, this is not used at all. Right, this is now going to be a big essay. So, in 4 part B, right, the immersion heater is now removed from the beaker. So on one end, we have a metal rod, and on the other end, a plastic rod, and they are both placed in the beaker of hot water as shown here, over here. Right, so one metal rod and one plastic rod. The rods are at room temperature at 20 degrees before they are placed into the beaker. So we have to describe how temperature of this point, right, change on each rod changes after the rods are placed in the beaker. We are to also explain our answer. Okay, so first thing first, we need to know, right, in a metal rod, this is a good conductor of heat. Okay, and over here, a plastic rod, it is a poor conductor of heat. So that means the heat from the water move up here faster and move up the plastic rod slower, and so point X on the metal rod should rise in temperature faster than the point X on the plastic rod. Okay, so this is your reasoning. Now we need to write everything in a nice big paragraph over here. So let's do that. All right, so let me just find my text. Right, so we first need to know, right, that point X of both rods increase with temperature over time. Okay, that's our first point. Okay, however, point X of the metal rod should increase in temperature faster than the plastic rod, because metal is a better conductor of heat due to delocalized electrons in the metal. Wow, my spelling is horrible. Hang on a moment. Better for you guys to read here. That looks pretty not very nice. So let's just put this down a little bit. Oh, here. That should be a bit better. All right. There we go. Okay, so basically, how do you get your full marks for this question? This is a 4-mark question, and it seems like you have to write a full essay for this, right? So the pointer is like this. So point X of both rods should increase the temperature over time. This gives you 1 mark over here. All right. The next mark, oh, I forgot one more thing. By conduction. My bad. Right. Sorry about that. Okay. So both rods will increase in temperature over time due to conduction. And that gives you, conduction gives you your 2nd mark, because of course this is heat transfer by conduction. However, point X on the metal rod should increase in temperature faster than plastic rod. And this gives you your third mark. Because metal is a better conductor of heat due to delocalized electrons in the metal. That gives you your fourth marks. This is how you get your full four marks for this question. So do you remember most Cambridge questions, right? They are very nicely structured. So if you were to hit all 4 points over here, you will be able to get your 4 marks easily. Okay? Right. So that with that, question 4 is done. So let's take a look at if there's any questions from chat. All right. Okay. So let's see. Oops, that's bad. Okay. Let's continue. Where is the standard one? Over there. All right. So sorry about that. Okay. All right. So from Mr. Abash Tapa, once again. Oh, there's another question. Okay. So can light other than sunlight, if it has sufficient energy, be used to generate electricity on the solar panel? You mean, right? Yes, that's a good question actually. It is this question is far beyond the Cambridge syllabus, but if the photon has enough energy to excite electrons in the photovoltaic material, yes, it can. All right. So thank you for the good question. That's fantastic. All right. I will now do a very short break, and I'll be back in 2 minutes. All right, welcome back. So now, if there's no other questions, let's move on with question 5 of this paper. Now let's move on. All right, so for this question, this is on dolphins. Okay, so this question asks, right, that a dolphin communicates with other dolphins by emitting sounds underwater in the range of 7 to 15 kilohertz. All right, so this is to do with the speed of sound and sound in general, waves, yeah? So 5 part A tells you to state the value of speed of sound in air and state how the speed of sound in water differs from the speed of sound in air. So Usually, we all do know that speed of sound in air is about in the ballpark of 330 meters per second. It could be plus minus 10 meters per second, as long as you're around 300. Yeah. And the speed of sound in water, as you know, water molecules are much closer together compared to air molecules. And because of that, the speed of sound in water is faster. It is higher. Right. Then speed of sound in air. Actually, you know what? You just need to write one word for this. Is higher. All right. Okay. So let's move on. All right. So next, what we need to do is we need to state and explain if humans with normal hearing can hear the sounds emitted by the dolphins. As you see here, the dolphin emits sounds from 7 to 15 kilohertz, right? Now, the human hearing is from 20 hertz to 20 kilohertz. So that means we can hear the dolphins underwater. Cool, isn't it? So we can hear the sounds, right? Yes. And hear the sounds. Sorry. Hi, Lily. Sorry, please make a move. We are having a lesson here. Okay. There you go. Yes. Humans can hear the sounds, right, made by a dolphin. And the explanation is very straightforward as well. As is seen here, dolphins emit sound with range within the human range of hearing, which is 20 hertz to 20 kilohertz. All right. All right. That's it. Simple and easy. All right. All good, yeah? Okay. Other than our very good friend here, Lily, she decides to join us once again for our lesson. So please don't mind when she jumps on the table, yeah? Okay, let's move on to part C. Right, so 5 part C, they want you to complete the table to describe the differences in loudness and pitch of 2 different dolphin sounds. Okay, so the frequency for the first one is 14 kilohertz. Okay, and amplitude, as stated over here, is large. So the first thing first, the loudness of a sound is dependent on the amplitude of the wave, of the sound wave. So if the amplitude is large, the loudness is higher, and if it's small, it's lower. So for the first wave, it is loud. And for the pitch, as you see over here, the higher the frequency, the higher the pitch. So 14 kilohertz is quite high, so we'll just write it down as high. As for the 8 kilohertz is the low option, and a small amplitude means it is soft. Okay. Hello, please get down. Thank you so much. You sit here then. You join me in the lesson. Okay. All right. So next, let's move on with part D. Okay. Now we are to complete the sentence to describe how sound is transmitted through water. Right, so this is very, very straightforward. Pretty much it's a free 3 marks for us. So let's move on. So sound waves are made of vibrating what? Sound waves are made from vibrating particles, which produce compressions and rarefactions. A compression is a region of what, and the rarefaction is a region of what? So usually a compression is region of high pressure, and the rarefaction is a region of low pressure. The sound waves will travel what to the direction of the vibrations? It actually travels parallel, because sound waves are longitudinal waves. And with that, you get your free 3 marks and your free 2 marks. This is probably one of the easiest questions that I've encountered in IGCSE Physics so far. Is everybody fine with that so far? Okay, looking good. Now, let's move on to question 6. Oh, over here. Okay. All right, so question 6, right? You show here part of an optical fiber that's used for high-speed broadband connection. So this is something that everybody nowadays cannot live without, isn't it? Right? So here we have to state 2 advantages of using optical fibers in high-speed data transmission compared to electrical signals on copper wires. All right, this is testing on a relatively new part of our syllabus, which is using optical fibers for communications. So there are we can use either of these advantages, right? So optical fibers can carry higher rates of data transmission, is able to carry larger amounts of data, it is more secure and less likely to be interfered, and there is also less signal loss or data loss. But of course, as you can see here, this is a 2-mark question. So please only write 2 valid points, okay? So without further ado, let's write down our answer. Our answer is also very straightforward. I'm gonna just do it right here. Okay, as you see here, optical fibers can carry higher rates of data transmission compared to traditional copper wires. This is your first mark. And they're also less likely to suffer signal loss compared to copper wires, and that's your second mark. Remember, 2 marks, 2 valid points, okay? All good? Now let's move on to part B1. Okay, part B1, you can see that the optical fiber is made of a glass with a refractive index, important words here, of 1.4. Now we have to calculate the critical angle C. So what is the critical angle, right? A critical angle is simply this is the optically denser solution, the denser part, and this is the optically less dense part. So your critical angle is the angle when light comes in here, right? This is the angle. And then the light actually does not exit here. It actually comes out parallel. Oh dear. It's not parallel with the medium here, the division between the medium here. So this is your critical angle over here. So to calculate the critical angle, right, C, we have this equation, sine C is equals to 1 over n. N is the refractive index, okay? And C is the critical angle. So we already have the refractive index of 1.4. So let's just do the equation, right? So C is equals to arc sine 1 over 1.4. And that gets you 45.4 58 degrees. And of course, let's convert this, let's round this up to two significant figures. 5 is equals to or greater than 5, so you get 46 degrees. Two significant figures over here. Okay? Degrees. Please write this down, yeah? Okay? So writing this down gets you 1 mark. Getting the correct answer gets you your 2nd mark. Good. Okay, so far, huh? All right, very good. Let's move on. Next, let's go to part 2, and we need to state the meaning of the critical angle. Oh yeah, we have already wrote the critical angle here. What exactly does it does, right? So let's just write it down over here as simple plain text. Right. The critical angle is the angle of incidence of light, right, from a higher to a lower refractive index where the angle of refraction is exactly 90 degrees. Okay, so as you can see over here, the critical angle is the angle of incidence over here of light from a higher to a lower refractive index where the angle of refraction is exactly 90 degrees. Right? Nicely clear. Very good. Okay, this is your 1 mark settled. Now let's move on to 6 part 3. On figure 6.1, we are to label the angle of incidence of the light ray of the ray of light as it hits the wall on the glass fiber, and we are to draw the continuation of the ray until it leaves the glass fiber. So, do take note, right, when a beam of light is going through this optical fiber, it is undergoing something called total internal reflection. Okay, for this, what it means is all right, what that means is that your oh dear, interesting. That's interesting. Hang on a second. Are you still working? Yeah, there we go. Fantastic. Okay, so that means your angle of incidence should be equal to your angle of reflection over here. So please hang on while I try to draw properly on a digital board over here. Let's say this is 90 degrees to the surface, and this technically should be something like this. Okay, the light goes here. Okay, this angle should be equal to this angle. Please remember that. And of course, same thing over here. You must have a nice straight line over here. And this angle should be equal to the angle of light right over here. That goes this way. Okay. Here. And of course another line here. And this should be the same thing over here. Just like that. So as long as your incident angle is equals to your reflected angle, right? Yeah, what happened here? So let me just press the back button for a second. 1, 2, 3, 4. Okay, that should do it now. So as your theta here is equals to your theta over here, you'll be good. Okay, same thing over here. Your angle of incidence equals to your angle of reflection. We are good. Okay, right. So how do you get your final 2 marks over here? First things first, we have to make sure that the angle of incidence and angle of reflection are equal due to total internal reflection. Make sure to draw the angle of incidence, which is over here, okay? And angle of reflector. And of course, the ray is to leave the optical fiber after 2 or 3 reflections. There are 3 here, so we are good. Okay, and that gives you your full 2 marks. All right, fantastic. Now we are done with question 6. Let's take a look at chat to see if you guys have any other questions. Okay, so far no questions, which is great, fantastic. I guess this is pretty simple for you guys as well. That's good to hear. Now in that case, let's move on with question 7. Circuits. Okay, let's move on. Question 7. All right, so for question 7, we see over here, there's a circuit with a 6-volt battery of cells with 3 identical resistors. Okay, so as you can see here, the switch is closed. Now the switch over here, S1 is closed for part A, and switch number 2 is open. The current and emitter is 0.080 amperes. So when you close switch 0 and you open switch 2, you can kind of, ignore this part of the circuit and just focus on this part of the circuit, all right? Because this is an open circuit, and what that means is resistors 1 and 2 are connected in series. Okay, so we have to calculate the resistance of resistor 1. So, yep, as you see here, see, one is open, one is closed, 2 is open. R1 and R2 are connected in series and they are identical. So we can calculate the total resistance of R1 and R2 using this very handy equation called V equals to IR over here. Okay, so now let's convert this in something you want. You want the resistance, combined resistance of R1 and R2 over here. So let's move I over to here. Let's divide both sides by I. So R will be equals to V over I. And we have V, which is 6 volts, the potential difference, whole circuit, divided by I, which is 0.080. And doing this, we get 75 ohms as a combined resistance, right? So we do know that this combined resistance is the sum of these two. So sum of the one resistor, since they are equal, we can just take 75 divided by 2, and that gets you 37.5 ohms. And if you want to, let's do it this way, 38 ohms, which is in 2 significant figures. As we do, please remember to do this. Okay, right? 38 ohms. Okay, now in part B, right? Switches 1 and 2 are now closed. Now you have to find the reading on this emitter. Okay, so what this means is the whole circuit is slightly changed. Okay, so this is our batteries up here now, right? Emitter is still here. Okay, but here's the thing, right? We can try and redraw this a little bit easier, like this. Okay, so as you can see here, this is now a parallel circuit where resistors 1 and resistors 2 are connected in series here, and then they are connected in parallel with resistor 3 down here. Okay, so we have switch 1 and switch 2 closed somewhere around here. Okay, so switch 2 is here, switch 1 is here, closed, all closed. Okay, so now we're supposed to find the current of the whole circuit. Okay, so what do we do? Okay, our first method is to calculate the current flowing in resistor 3. Even noticing is this circuit is in parallel, right? The voltage across resistor 1 and 2 is still 6 volts. The resistance across resistor 3 is also 6 volts. Okay, so which means the current over here, R1 and R2, is still 0.080 volts. So let's just do this. Okay, let's do current in R1 plus R2 is equal to 0.080 amperes. That's the first one. Now we have the current in R3, right? So we do have our V equals to IR. Okay, that's the IR. We now want I to be the focus, so let's divide both sides by R. We get I equals to V over R. Okay, equals to V over R3. Okay, R3 is 38 and V is 6. So let's do this. 6.0 divided by 38 and you get 0.157 amperes. Okay, now we need to find the total current, which is this current in R1 plus R2, and add it with this current. So total current equals to 0.080 plus 0.157, and that gets you 0.237 amperes. And of course, let's do the rounding up, which you get 0.24 amperes in two significant figures. Right. Pretty simple, isn't it? Okay, this is our first method. Okay, and of course, how do you get the 3 marks? The 3 marks you will first get when you determine what is the current in resistor 3, the current in resistors 1 and 2, and last but not least, getting the correct answer over here. And that gets you your full 3 marks. Okay, there's actually a second method which is also pretty simple to do. We can actually find the combined resistance of this whole resistor, this whole bunch of resistors over here. So, as you remember, 1 over R total is equals to 1 over R1 plus 1 over R2. In this case, 1 over R1 is equals to 1 over R1 plus 1 over plus R2 over here. So, excuse me. Yeah, I've run out of space. Okay, let me just rewrite this nicer so that you guys have a bit more, can see, don't have to see my ugly handwriting. So 1 over R total will be equals to 1 over R1 plus R2, which is the first here, plus 1 over R3. And with that, if you do the calculations, it's 1 over, okay, and then R in total should give you, in total, 25.2 ohms. And then, if you do V equals to IR, same thing again, you should get the I is equals to V over R, which is equals to 6 divided by 25.2, which also will get you 24 amperes, 0.24 amperes, right? So this is method number 2. Okay. Either way works as long as you get the correct answer and do the steps correctly, slowly and carefully. Okay. All right. Okay, now let's move on to this part 2. Okay, so for B part 2, we have to explain in terms of work done and potential difference why there is a larger eating effect in R3 than in R1. So we have to explain in terms of work done and potential difference. All right. So do take note, right, over here, right, switches 1 and 2 are closed. And the potential difference across R3 is basically 6 volts, while the potential difference between R1 and R2 is basically 6 divided by 2, which is 3 volts across R1 and 3 volts across R2. Okay, let's write that down. Okay, simply put, here. Right, as you can see, the potential difference across R3 is twice that of R1, and thus more work is done by the charges passing through R3. As we stated over here, the potential difference across R3 over here is 6 volts in full, while in R1 it is 3 volts and R2 is 3 volts. So there's greater potential difference across R3, and because of that, more work is done by charges passing through R3 compared to R1, actually twice. Okay? Yeah, so with that done, I think we can move on with question number 8. Oh, a solenoid. All right. So question 8 shows a solenoid, and for question 8 part A1, we are to draw 4 complete magnetic field lines to show the pattern and direction of the magnetic field inside and outside the solenoid. Okay, so this is an electromagnet in essence. So let's just draw that. So we are to draw 4 complete magnetic field lines. Okay, so the first line, we just have to draw this way. Okay. My goodness, this is horrible. The lines has to be this way. Just remember, this is kind of parallel inside here, yeah? Then the last 2 lines has to go this way. The line has to go this way. Okay, make sure all these are equally spaced apart. All right, now we have to determine the direction of the magnetic field lines. So for this is the coil, and we need to determine where is the current flowing. This is the positive, this is negative, so current flows this direction and contact from this direction. So as the current flows this direction, right? So we kind of want to have our right hand rule facing in, let's say, as you see, using your, I'll do it with me together. Hold your right hand, grab it will the current as our fingers, it goes upwards and it curls around the coil. Okay, this is our right hand grip rule. So our thumb, which is what the where the direction of the magnetic field north should be, is pointing towards your left. Okay, so this is the direction of the magnetic field lines, and thus we put the arrows this way, like this, and the arrow should point into the solenoid. Okay, all right, so this should get your full 4 marks. So first things first, we need to, how do we get the full 4 marks? Number 1, using the right hand grip rule, we need to find where is the field line is going to point. That's our first mark. Number 2, right? The pattern must be symmetrical. This is a very bad example. So after this whole lesson is done, please feel free to download the completed lesson PDF that I will have drawn nicely for you guys. So please use that instead, okay? Yeah. The pattern must be symmetrical and the lines must curve out of the solenoid. So basically, these two lines must be symmetrical. These two lines must be symmetrical. Both sides must be symmetrical as well. And of course, 4 lines must be drawn. Doing this, you should have your full 4 marks. Okay? There we go. Now, A part 2, you have to mark a point inside the box, this dotted line box over here, where the magnetic field is strong. Label this point B. Okay? So, the magnetic field is the strongest, right? Just outside the coil, like this, over here, all right, at one end of the coil. So it could be here, it could be here, but not inside, okay? Yes, the lines are closest together inside here, but you cannot really measure anything inside here, yeah? So we want to have B, right, B over here, or over here, or over here, or over here. Either one of these 4 will be fine, okay? Okay, now we are to explain, right, why the magnetic field is strong at B. Okay? The magnetic field lines is strong. A magnetic field is only strong when the magnetic field lines are close together. Okay? So when the field lines are further away from each other, it is not as strong. Right? So let's write that down. Okay? Hi Lily, please don't disturb. He's back again. It's me. Okay, so please don't sit here. I need the touchpad. The magnetic field lines are close together as the magnetic field line the field is strong at B. Okay. All right, fantastic. Okay, so come on, please don't sit over here. I guess Lily wants a PhD in physics. All right, so let's move on. Okay, A part 2 done. Now let's move on to question 8B. Okay. Oh dear, where's my pen? That's wrong. Okay, give me a second. I have a slight issue with my with this. Give me a second. All right, 1 second. Let me just handle this for a while. This worked. Oh, that was better now. Fantastic. Okay. Sorry for the slight issue. It should be good now. You can go now. All right. There's something wrong with my tablet. All right. Let's move on. Part B. All right. So part B, we see a solenoid in an electric circuit for a bell. So you can see here, the solenoid over here is connected to a circuit and connected to a bell. So we are to complete the circuit at figure 8.2 with a symbol for a direct current power supply. Okay, so a power supply, there are two types. There's a alternating current, which looks something like this, okay, and a direct current like this, which you need to identify which is positive and which is negative. In this case, we want the DC one, which is over here, okay, AC/DC. Thunder. So DC, we want to draw these total circles over here first, and then we want to add the plus sign here and the minus sign here. Why? Simply because the positive terminal should be connected to the switch at most times. Okay, this is just by our standards. Okay, when you just write this is the DC power supply. You should be able to get your full 1 mark. Okay. Next, part 2, B part 2, we need to explain why the soft iron arm pivots and making the striker hit the bell when the switch is closed. Alright, so when you close the switch over here, it activates this solenoid over here. This solenoid will attract this arm downwards, and as a result, the striker will hit the bell. Okay? That is how the whole thing works. So, once again, let's write in our explanation. Okay, so basically, when the switch over here is turned on, the solenoid becomes an electromagnet, and this solenoid would induce, or should I say, attract this soft iron arm and make it attract to the solenoid, and because the striker is connected to the soft iron arm, it moves downwards and hits the bell. Pretty easy, isn't it? And that gets you your full 2 marks. Oops, my bad. Draw this, okay? Yeah. So, last but not least, part 3. We have to explain why the arm pivots back to its original position after the striker hits the bell. Okay, so as this thing, right, as you see, as the striker hits the bell, this thing is attracted over here. Notice there's a contact over here. So as the soft iron arm moves downwards, right, the contact, which actually closes the circuit, actually opens. Alright, this actually breaks the circuit, and that means the solenoid becomes demagnetized. Alright, and when this is demagnetized, the soft iron arm stops working. The solenoid stops attracting the soft iron arm, and thus the striker, and the thing is, the soft iron arm moves backwards via the springy metal, and the striker moves backwards. All clear? So let me repeat it one more time for clarity. When the solenoid attracts the soft iron arm and the striker is down here, the contact, which actually closes the whole circuit as well, is open. This breaks the circuit, and the solenoid stops being magnetic, right? And because of that, the solenoid stops attracting the soft iron arm, and the soft iron arm, due to this springy metal, goes backwards to its original position. Okay, this moves the striker back upwards and doesn't hit the bell. Okay, now let's write that down. Lot to write. Thus, I have to do this on the side, if not this will take too long. Right, so let's take a look at our answer. So when the soft iron arm is attracted to the solenoid, it breaks the circuit, simply because there's a contact over here. As the current is broken, the solenoid stops being a magnet, and the soft iron arm over here loses its magnetism. This allows this springy metal to push the iron arm back into its original position. Okay? Right? And because of that, as long as you have any of these two valid points over here, you should get your full 2 marks. All right. That done, let's move on to question 9. But okay, before that though, are there any questions from chat that you'd like to ask? Is everybody okay down there? Okay, everything is looking good. Right, let's move on. Since there's no other questions from chat, I think we can move on to the final 2 questions for this paper, which is question 9 and 10. Okay. All right, let's move on to question 9a. So we are to describe the nature of an atom of helium-4, which is 4,2He. So an atom of helium, right? If you all remember, consists of 2 protons, 2 neutrons, and 2 electrons. Okay, orbiting, right? So pretty much we are to describe the structure. So let's write that down. Okay, so a helium-4 atom consists of a nucleus with 2 positively charged protons and 2 negatively charged neutrons, as you can see over here. 2 protons, 2 neutrons. This nucleus is surrounded by 2 negatively charged electrons. Okay, so yeah, 2 protons which are positively charged, 2 neutrons which are neutrally charged. Okay, negatively charged neutrons. What am I writing? My bad. Excuse me. Wait a minute. 2 neutrally charged neutrons. Okay. All right. And this nucleus is surrounded by 2 negatively charged electrons. All clear, yeah? Good. Okay. Now, let's move on to 9 part B. 1. All right, our sun is a medium-sized star powered by nuclear fusion reactions which release energy. States what happened during nuclear fusion which form helium. So I think this is something that is quite familiar to everyone. Our sun uses hydrogen to undergo nuclear fusion to produce helium, right? So pretty much we want to write like this. Right, so we have to state what happens in nuclear fusion, state what happens during nuclear fusion reaction to form helium. So for a nuclear for a nuclear reaction in a star, hydrogen nuclei join together to form a helium nucleus. That is our answer. So pretty much, right? Pretty much for this question, see, okay, for this question, hydrogen nuclei joined together gives you 1 mark over here, and to form a helium nucleus like that gives you 2 marks. Okay, so that is your full 2 marks, easily gotten like that. Okay, easy, yeah. Okay, 2 marks. Done. And now in B, part 2, we have to state 2 regions of the electromagnetic spectrum by which the sun radiates most of its energy. Alright, so of course the sun radiates most of its energy via visible light, right? Next to it, we have, of course, visible light is a very small part of the spectrum. That so visible light is here. Okay, what's beyond violet or visible light, you get ultraviolet, and what is before red, you get infrared. So we kind of know that the sun emits mostly in the visible light area and the ultraviolet region. So let's also write ultraviolet. Okay, these are the 2 acceptable answers for this part. And naming both of that will give you 1 mark each. Okay, now let's go to part C. Oh, you're testing here about astronomy already. So describe what happens to a star where most of the fuel in its center or its core has been converted into helium. Okay, so over here, let's do it this way. All right, so there are 2 types of stars. You have the normal main sequence like our sun, and you have the big stars like, you know, Rigel or something, big blue stars, giant stars, right? So when our star like our sun runs out of hydrogen, it becomes a red giant. When a giant star runs out of hydrogen, you get a red supergiant. Okay, so what happens to a star? Let's write down the answer. When the star's core runs out of hydrogen, smaller stars like our sun expand and become red giants, while larger stars expand and become red supergiants. Okay, pretty simple, yeah? Okay, one of the simpler questions for this. Okay, and these 2 marks are pretty simple as well. 1 mark for stars like our sun, smaller stars, this gives you 1 mark, and bigger stars get you our 2nd mark. Okay, yeah, pretty straightforward over here as well. Okay, yeah. Now let's move on to our final question. Question 10. Okay, so in question 10, right, question 10 shows the orbit of the Earth and the orbit of a planet around the Sun. Okay, that's a very strange looking orbit, look like a sausage. So for part 10a, we have to state which orbit, A or B, is the orbit of the comet, and we have to explain our answer. Okay, as you do know, comets have highly eccentric orbits. Yes, highly elliptical orbits. As for A, right, which is a nearly circular orbit, I'm very sure this is the Earth, yeah? And this is the comet. So, orbit of comet is orbit B. And here we have the explain why. Alright? The explanation is also very, very simple. As I stated before, comets are known to have highly elliptical orbits. Okay? There you go. That's your easy 1 mark. Done. Alright? Pretty straightforward, isn't it? Okay. So let's move on to part 10b. So we are to describe and explain how the motion of a comet changes as it orbits the sun. The key here actually is not really about how fast and slow it gets, but we want to also, talk about the energy states over here. So let's talk energy, yeah? When the comet is far away from the sun, right, it's very, very, very high up. So it has higher gravitational potential energy, right? And its kinetic energy is very low. Well, when the comet goes near the sun, like this, right, it moves this direction, okay? It has low gravitational potential energy, but it has high kinetic energy. What that means is the comet moves very slowly here, and the comet moves very quickly here, nearer to the sun. Okay? Right. So this is what we're going to write down here. Describe and explain. Right? So first, let's describe what happens. Okay? The comet, okay, moves faster as it gets closer to the sun. This is because comets have highly elliptical orbits, and when it is closer to the sun, its gravitational potential energy is converted into kinetic energy. Okay, energy which increases. Okay, the former decreases and the latter increases. So basically, gravitational potential energy, when it comes near to the sun, right, it decreases, and kinetic energy, as it gets closer to the sun, it increases. Pretty straightforward, yeah, this one. Okay, although this is not the easiest question to do, should be quite straightforward. Okay, and just like that, you get your full 2 marks. Okay, let's move on to a 10 part C and C1, right? At one position of its orbit, this comet is 6.6 times 10 to the power of minus 6 light years away from the Earth. This is quite still a big number, yeah? So we are to state the meaning of a light year. A light year technically is a measure of distance. It's not how fast light travels, it's not how quickly, how speedy light is. It's actually the amount of distance, the distance that's traveled by light in a year. Okay, so let's write that down. This is very, very straightforward as well. 1 mark, right? Okay, light year. I should have hyphen here. Light year is the distance traveled by light in 1 year. Done. Pretty straightforward. Great. Now let's move on to C, part 2, the last part of our session today. We are to determine the distance in meters, all right, between the comet and the Earth when it is 6.6 times 10 to the power of minus 6 light years away. All right, so let's do it. We do know, actually, give me a second. Are we given 1 light year? No, we're not. But the thing is, you are supposed to remember it. Okay. Okay. So determine the distance between Comet and Earth. So 1 light year is equal to 9.5 times 10 to the power of 15 meters. Okay, so now we are given that the comet is 6.6 times 10 to the power minus 6. Okay, so light years away right now. So 6.6 times 10 to the power of minus 6 light years will be equals to, okay, 9.5 times 10 to the power of 15 meters multiplied by 6.6 times 10 to the power of minus 6. All right, and we need to do some really complicated mathematics. Actually, just please press your calculator slowly and carefully during this time. This is a very tricky calculation that you can get careless. So please be careful. When you do the calculations, you get 6.27 times 10 to the power of 10 meters. Of course, let's round this up to 3 significant figures. To 2 significant figures. You get 6.3 times 10 to the power of 10 meters. Of course, 2 significant figures. Okay? And with that, we are done with this part. Of course, when you write down this part over here, you get 1 mark. Getting the correct answer gets you a second mark. And total, you get your 2 marks like that. Okay? So I hope this is clear for everybody. Yeah? Should be quite straightforward. Okay? All right. So are there any questions from anyone in the chat? We are kind of done with our session today. Any questions from chat that you'd like me to answer? Okay. Looks like there are no further questions. Thank you everybody so much for joining us in our... Right, I think no questions from our answer as well. I think that's really about it. So with that, I would say that's it for our session today. Thank you so much for coming to our humble little session. It is a pleasure being your teacher, and you guys are a fantastic audience. Hope to see you soon. Goodbye.